Excuse me. Let's take a look at how we determine rate. So we have our data table here. We've got from 20 seconds to 40 seconds. So 40 minus 20 is 20 seconds for the bottom. That's our time. That's our change in time. Our change in rate, we're going to find the rate for 40, which is 0.426, and for 20, which is 0.355. 0.426 minus 0.355.
It's 0.071.
0.071, and that's molarity. So basically change in concentration or change in molarity. So we take 0.071 divided by 20.
It's 0.00355.
Molarity per second. And what you're going to see as you keep going, the change in molarity keeps going down. Why do you think the rate decreases as time goes on? What causes a reaction to happen? The reactants have to collide. As time goes on, why does this decrease?
It loses the energy.
Well, that's possible, but there's a bigger calling on this. Right now, you guys are sophomores or juniors, I think, and maybe a few seniors, but who has a date to next year's prom right now? Probably not many people, maybe one or two, right? So right now, there's a lot of people that need a date for next year's prom. As we get closer to prom, what happens to the number of people that need a date? It goes what? It goes down. Same thing's happening. At the beginning of this reaction, we have so many reactants and they can collide easily. As time goes on, the reactants become products. So there are less reactants to actually collide with each other. So the rate decreases. Same thing. From 10 to 40, that's 30 seconds. 0.426 minus 0.246.
It's 0.18.
0.18 divided by 30 seconds. 0.18 divided by 30.
It's 0.006.
There we go. This is closer to the average rate. Now, if we want the whole average rate, we take the entire amount of time, which is 50 seconds, and we divide it by the entire change, which is 0.35. 0.435 divided by 50.
The answer is 0.0087.
Well, there we go. And then you were to answer the questions dealing with these guys right here. See if I can get a better focus on this. So what do we got? Figure 1, endothermic or exothermic. Here is the energy of the reactants. Here is the energy of the products. Endo or exo. Products have more or less energy than the reactants. Yeah, so you're saying that 6 is less than 2. So it's less, so that means that what's happened? We've lost energy, and it is exothermic. What letters represent the activation energy of the forward reaction? So if we're here, we need to get up to here. And that would be A. What letters represent delta H? Well, that's the one we just talked about. We had this much energy. We ended up with this much energy. So that would be D. What does letter C represent? That's the potential energy of the products. What is the activation energy of the reverse reaction? So if we imagine that this is a roller coaster ride that goes forward and backward, then to get up this hill, we need that much energy, which is E. This is the forward way, is A. The reverse is E. What does B represent? That's the potential energy of the reactants. How much energy does the activated complex have? That would be C plus E, or B plus A, or we could just go with 11 kilojoules. How about this one? Do we gain energy or lose energy? We're at 5, we're at 8, so gain, so it's endothermic. What is the activation energy of the forward reaction? Forward reaction, activation energy. We don't have an actual level, so we have to count it. 5, so 1, 2, 3, 4, 5, 6, 7, 8. What does the letters represents the activation energy of the forward catalyzed reaction? That would be F. Remember, the catalyzed reaction is the dotted line. What does G represent? That's the catalyzed reverse reaction. Activation energy. How much energy does the activated complex have? That's easy. That is J. What is delta H of the forward reaction? 1, 2, 3. 3 kilojoules. What is delta H of the reverse of the forward? What is delta H of the forward catalyzed reaction? Let me check that again. I don't think that's 3 kilojoules. What did I do there? 1, 2, 3, 4, 5, 6, 7, 8 kilojoules. Oh no, I'm sorry. It is delta H. So it is 1, 2, 3. What is it of the catalyzed reaction? 1, 2, 3. Doesn't change. Same delta H. Now it's our turn to draw these. So if we take a look, plot the energy diagram. Potential energy of the reactants, 250. Potential energy of the activated complex, 350. Potential energy of the products, 300. We're going to go something in the paper there. Oh, back there. Endo or exo, we gained energy. That's endo. What is the delta H value? 50 kilojoules. Easy enough. Check your answers on that one. Potential energy of reactants is 200, 100, 200. Potential energy of the activated complex is 400. And delta H is plus 150. So it's endothermic, 150. Boom. Endo or exo, since delta H is positive, that is endo. What is the potential energy of the products? That is 350. 350. Kilojoules. Boom. That is it for this. I'm going to stay on the Zoom and go through this reaction rates review, which I will then put as answers. If you want to try this and then check the answers, you're more than welcome to come back and watch the finish of the Zoom. I'm just going to talk through all of these problems. If you do find that you go and try some problems and you want to come back in and you have questions, by all means, drop back in. Otherwise, you're more than welcome to exit out and work on this on your own and then come back and check your answers. Have a great day. Have a great weekend. Remember, no Zoom on Monday. It is the test over this. So make sure you do come back and check this Zoom out later. So as a reaction occurs, the amount or concentration of reactants decreases. That's what we said about the dance. As time goes on, as you get closer to the dance, the amount of people without partners is going to decrease. So the reactants are what form the products. They decrease as time goes on. The amount of products increases. So this would be the number of people with like couples going to the dance. Increases as you get closer to it. In order to determine the reaction rate, you can measure either a decrease or change in concentration. During a particular time. That's that formula, change in concentration divided by change in time. That equals rate. Factors that affect reaction rates are, well, the biggest one is temperature. Temperature, the higher the temperature, more energy, faster moving particles. So you're going to have more collisions, and since they have that energy, they're more are likely to be successful. Concentration. You have more particles per volume. You're going to have more collisions. Surface area. That's similar to concentration. You're going to have more particles exposed. With a bigger surface area. Now, if you have a smaller surface area, like for example, let's imagine you have a big chunk of wood, it's not likely you're going to be able to catch that on fire because you don't have enough particles being exposed and easily in contact with the other chemicals required. If you lower the concentration, then you'll have less particles. So you'll have less, let's do more particles, more collisions. If you have less particles, it would be less collisions. Lower temperature, you would have less energy, so less would be successful even if they collide with the proper orientation. And they'll be slower moving, so there'll be less collisions overall. Last one is the catalyst. The catalyst decreases energy required, which we call the activation energy. By creating a new pathway. According to the collision theory, two things must happen in order for a reaction to occur. They must collide with proper orientation. And they must have enough energy. What is the activation energy? It's the minimum energy needed for a success. Let's put needed for the formation of the activated complex. The activated complex, if you recall, is that intermediate state. Oh, look at that. What is the activated complex? It's the transition from reactants to products, or the intermediate state, or the transition state between reactants and products. Explain using a collision theory why increasing temperature increases rates. Particles move faster. And collide more often. They also have more energy. Therefore, they most likely have the activation energy. How does the catalyst increase the reaction rate? Lowers the activation energy. by creating an alternative pathway. Cool. Last thing, make sure that you can do these things. I can list the factors that affect reaction rates and explain how using the collision theory. Remember, everything that you put here, there's an increase or decrease. Even a catalyst speeds up reaction. By lowering the activation energy. There is another substance that's the opposite of a catalyst. It's talked about in the videos that you watched Monday. It's called an inhibitor. An inhibitor, what do you think it does? Yeah, right? Slows it down. By blocking pathways. We could also decrease temperature. So I'm gonna just make it slower, make reactions slower. We're decreasing temperature. So we're gonna put a down arrow in temperature, less energy, and move slower. If they're moving slower, there's going to be less collisions, and if they're less energy, there's going to be less successful collisions. Low concentration or decreased concentration. Less particles to collide. On the back page, we did how to make it faster a lot of times. Less particles to collide. So on the front page, we're just going to make it how to slow it down. Decrease surface area. If we have less surface area, like a big blocky thing, less particles exposed for collision. I can draw and identify the parts of the rate law below. So if we take a look, we should be able to say A is the energy of activation. B is the potential energy of the reactants. C is the potential energy of the products. D is the delta H. Is it endo or exothermic? Endo or exo? It is exo, thank you. E is the energy of the activation. This is for the forward reaction. This is for the reverse reaction. If we were to have a catalyst, it would look like a dotted line. It would not affect D, which is the delta H. It would only affect the activation energy of both the forward reaction and the reverse reaction, and it would lower it. I can distinguish the difference between a catalyst, increases rate, and an inhibitor, slows rate. Cool, cool. I will post the answers to this entire packet shortly after while this video is rendering, actually. Those at home, do you have any questions?